Hello everyone, today I'm so glad to share our paper, Deep Constrained Least Squares for Blind Image Super Resolution. This work was done by Megvii Technology, Kuaishou Technology, and UESTC in collaboration. The code and pre-trained models are already publicly available. The BlindSR model assumes that the LR image is obtained by blurring a HR image and then downsampling it and add some noises, given by the following formulation. For most BlindSR methods, they'd like to first estimate the blur kernel, and then restore the high-quality image based on that kernel. They usually use both the image loss, such as L1 loss, and the kernel loss to optimize their networks. However, we noticed that there are two problems among current BlindSR methods: kernel estimation and kernel usage. First, note the ground truth kernel is effected on the HR image, and we can hardly directly estimate the blur kernel from LR image due to the ambiguity produced in the undersampling. Second, most BlindSR methods adopt a kernel stretching strategy, in which the kernel would be vectorized to one dimension, and then apply PCA and stretch it to be the same size as the LR image. But this strategy destroys the spatial relation of the kernel and thus causes an insufficient usage of the kernel. Address these problems. Our work proposed the deep constrained least squares for blind image super resolution. There are three contributions in our work. First, we reformulate the classic degradation model so that we can make the kernel estimation more reasonable. Second, we design a dynamic deep linear kernel module which could better estimate the kernel. Third, we propose a deep constrained least squares deconvolution module which can perform deblurring in the feature space and make use of the kernel. There is a visual comparison between our method with other state-of-the-art BlindSR approaches. As we can see, our method can recover sharp and rich details. Here is the degradation model reformulation. We want to convert the high-resolution space kernel to low-resolution space. To do that, we firstly reformulate equation 1 in the frequency domain to get equation 4, and equation 3 is the reformulated kernel KL. For numerical stability, we also add a positive small number epsilon to the denominator as equation 5. Then we can estimate KL from the LR image, as the examples below. Based on the new degradation model, we would like to estimate the kernel first. For this purpose, we design a dynamic deep linear kernel, DDLK. Instead of directly estimating a single kernel, DDLK choose to predict a group of filters with different kernel size, and preserving their receptive field to 21. Then we can convolve all filters with an identity kernel to get the final k-hat. In this way, we are able to estimate more accurate blur kernels, and we will show it in the experiments. After we got the estimated kernel, the next step is to apply a deconvolution method to get the clean image. Furthermore, we derivate a deep deconvolution module which could be applied to the deep feature space, named DCLS. First, we rewrite the degradation model in the feature space as equation 6. Our goal is to get the deblurred clean feature R-hat. To solve it, we introduce the Lagrange function and can derivate it to equation 10. We also noticed that the smoothness of each channel can be very different, so we use CNN to predict the smooth filter for each channel. Then we can explicitly get the deblurred feature by equation 11. This is the overview of our framework. Given the LR image, we will first estimate the blur kernel using DDLK and meanwhile extracting the deep features by several resblocks. Then we use DCLS to get clean features R-hat according to the equation 11. After that, the original feature and the clean feature are sent to a dual-path attention network to obtain the HR image. Note, since the feature is extracted by the nonlinear network, we design the dual-path network to compensate the artifacts and errors introduced from deconvolution. In this experiments, we evaluate the proposed method on two public datasets, Gaussian 8 and DEV2 KRK. For isotropic Gaussian kernels, our method achieves an ART performance in terms of PSNR. For anisotropic Gaussian kernels, we still achieve a new ART performance on DEV2 KRK. The results of estimated kernels also indicate the proposed DDLK is powerful in kernel estimation. Our estimated kernels are closer to the ground truth kernels. This is the visual results on isotropic Gaussian kernels. And this is the visual results on anisotropic Gaussian kernels. As we can see, the SR images produced by our method are much sharper and cleaner. Thank you for your attention.